Bloom. I'm from George Mason University. I'm presenting our work on differentially private access patterns in secure computation, which is a joint work with my PhD advisor, Dr. Dov Gordon. So many of these logos and organizations might be familiar to you, and it seems they are so unrelated, but they all have something in common. Can you guess what is this?
Breach.
Exactly, data breach. And in the recent attack that just happened a couple of days ago, this time attackers targeted the US Department of Defense, and they lost almost 30,000 of their employers' data. So what is the fundamental problem behind all of these type of data breaches? And why we are not able to solve them? So the reason get back to this fact that users generate huge amounts of data which are mostly sensitive, such as medical or financial records. And different service providers look at this data in Clear and run some machine learning algorithms on that to provide some services for us, such as movie recommendations or targeted advertisements. But at the same time, they put the user's data at the risk of data breach. So it turns out that cryptography can come to help, and if we can encrypt users' data, we can design some mechanisms to compute unencrypted data, which are called secure computation. So in that case, we don't need to trust a single party to take care of our data while they are computing on that, because secure computation makes it possible for multiple parties to do a functionality on their joint private input without leaking any information about this input to the other parties. But unfortunately, among 13 billion records that have been leaked during the last couple of data breaches since 2013, there are only 4% of them were encrypted and kind of useless to the attackers. So as someone working in security, and especially cryptography, you might think, why so few of the records have been encrypted? So it could have many reasons, but the reason that come to mind after reading the answer of this Yahoo's vice president to Senate after that their famous data breach, it seems that doing computation on encrypted data is very time-consuming and very expensive, and most of the time it's prohibitive. So that's why they are not using it in practice as it should be. So in this work, we try to answer this question that can we do these computations faster and make it more practical to be used if we allow something small to be learned by the attacker, and then we prove that what is learned is differentially private. So in this work, we are the first to show, we are the first to explore this relaxation in secure computation, and we also identified a class of computations that could benefit from this relaxation. So to see our improvements in action, since in US they are going to have their first electronic national census in less than 2 years, and they're expecting to have a huge data breach. So I used a similar computation, which is a counting problem, or we call it Histogram Problem, in which we want to count the number of different elements in a large data set in our computation. So imagine we have two untrusted computation servers that one of them could belong to Amazon, the other could belong to Google, and each user contributes a single input value from these three different colors, red, green, or blue. And this data, we imagine they are secret shared or encrypted and submitted to one of these servers or both of them. And the reason is we don't want any of these servers to have a full control over the user's data. Then they involve into a interactive secure computation process and compute this counting problem. And the output, which is also a secret shares, contains the exact value of the counter values. So keep in mind that actually, unlike the usual practice that they use in the differential privacy, we don't add the noise to the output. We are having the outputs secret shared, which is secure already, and they are the exact count of the data for each type. So if we look closer to this computation, even we keep the input and the output private, which means they are encrypted or secret shared, the computation servers still can learn a lot from the computation itself while accessing the data, right? So without knowing what were the content of those elements, the input elements, the attacker could exactly see what was the number of elements, for example, I, first, second, or third. So the first question that we asked ourselves was how we can hide this access pattern. So there are so many works in the literature was targeting to solve this problem of hiding access patterns. But the simplest one is when we are reading or writing one single element in the input array, we are touching all the other elements to hide which one was our exact target. So this solution, it has a linear cost per access. So when we are dealing with big data, usually it's very expensive and prohibitive. But there is a more clever way to do it, which is using ORAM, or called oblivious RAM, which translates each access to multiple accesses to hide which one was our target and which one was the real one. And only one of them is real. So ORAMs, they have their own line of research, and there are so many improvements have been done in recent years to reduce its overhead and its cost. But still, this solution costs polylogarithmic per access, and still it is expensive for us, to be practical. There are so many tailored solutions for this problem of hiding access patterns, and as a more generic solution, Nayak et al. Showed that they could do better than ORAMs, and they reduced this cost to n log n asymptotically and n log s square n for practical parameters, for a class of algorithms that can be modeled as graph parallel computations, for example, doing MapReduce on large dataset. You might have heard of it. Note that all of these solutions that I mentioned so far, they are fully oblivious and they provide full security for this problem of hiding access patterns. So, as you might guess, those solutions are very expensive for the practical use. So in an attempt to find an alternative for these expensive aforementioned solutions, in this work, we want to allow some leakage and provide a formal guarantee on the amount of data that is learned. Therefore, we looked at differential privacy, which has been used before in the literature to provide data privacy and protect the data by adding differential private noise. And actually, as you can see here, in all of the Apple summits, maybe 2016 or 17, they were using this differential privacy as a hammer to sell their products, saying we are protecting the user's privacy by differential privacy. So keep in mind that differential privacy is a separate orthogonal question from secure computation, since they are traditionally two different areas and are concerned with two different problems. Differential privacy is concerned with what is learned from the output, but here what we care about is what is learned from the computation itself. So this picture shows our security definition, which it is a real-world view versus ideal world. And it illustrates that the adversary will receive more information than the output. And we prove that this leakage function L preserves differential privacy. But before going to the details of our construction, I'm going to show you the final results and give you the taste of what you can achieve with this relaxation. So we could improve the previous result that Nayak et al. Achieved by log factor, which has a huge impact when we are dealing with big data. And our results demonstrate that with differentially oblivious algorithms, we can achieve better performance asymptotically as well as for practical parameters as compared to fully oblivious solutions. So in this case, you can see we achieve linear overhead for asymptotic results and only n log n overhead for the practical parameters. Here, alpha is a parameter that we tune it by it depends on the differentially private parameters epsilon and delta. N is the number of counters, which are the number of types that we have in our dataset, getting back to the histogram problem, and n is the size of the input or dataset that we have. So getting back to our histogram example, I want to walk you through to the process to show you how we achieve this improvement. So using a single bit, so in GraphSC, what they did, they concatenated the output array to the input array. And they use a single bit to differentiate between the input and the output element. And keep in mind that I'm showing the content of these arrays to you, but they are all secret shared or encrypted in the server. So the server doesn't see the content of this input and output. Then what they do, they sort this array based on the colors and also based on those flags or bits that they use to differentiate between the output and the input. So they sort them in a way that they put these counter values or the output values at the beginning or at the end of this subarray for that particular color. In the next step, they just do a linear pass, which is a data oblivious operation, just doing a linear pass on this array and run the counting operation inside of the secure computation. As I show it here with a blue computer, it's just doing oblivious operation. So here you can see that we actually hiding access pattern because we are doing a single pass on the whole all the elements in the array. So then we thought that what if we just generate some random elements and mix it to this input array and just let the access pattern to be revealed by the attacker. So by that, I mean, so let's imagine we generate some dummy elements from the input array and we concatenate them with the real elements that we have. But of course, keep in mind that this dummy generation operation, we don't have a trusted party to do it for us. So we have to do everything in secure computation. So that is why I'm showing it in a blue box. And then we also assign a single bit to differentiate between the real elements and the dummy elements in this array. We are replacing their expensive operation, the sort operation, which takes n log square n in the practical parameters, with an oblivious shuffle, which only takes n log n. And as you can see, the dummy elements are mixed into the real elements. And from the adversary's perspective, he doesn't know how many dummy elements we have per type and where are they located in this array because they are all shuffled. And this shuffle is also done in the secret or secure computation. So here, by just hiding those bits, I'm showing you that the array itself, it can be revealed to the attacker. So the attacker could see the access pattern that we make. For example, we are touching the blue counter or the red counter or the green counter. But what attacker knows is that these values, these elements, he doesn't know which one is real, which one is dummy. So we made a very interesting observation, which is the access pattern to memory is still leaked in our solution, but it exactly follows a histogram problem, which is a canonical example in differential privacy. So the dummy elements that we added to the input array, it is makes it a new noisy histogram, which preserves differential privacy. So then we asked this interesting question that what kind of computations can benefit from this relaxation? What type of computations have this type of histogram pattern when we are doing access pattern? So we looked at the same computations that Graphically looked at them. And some of them are very famous in the machine learning community, like MapReduce, GraphLab, or PowerGraph. And as you can see here, we can model any problem that we have in, for example, real world into the graph model. For example, here we can model the histogram problem to the bipartite graph. We have users on the left, counters on the right. Or in this case, we can model the matrix factorization problem that is usually used for movie recommendation systems. So on the left, we have the user elements. On the right, we have the nodes for the movies. And the edges contains the ranking that each user made to a particular movie. So what they did in those frameworks that I showed you, they translate or they break down all of the operations that we can do on those frameworks into three main phases, main operations. The first operation is called gather operation. So in the gather operation, we imagine in the graph, we are gathering all the information from the incoming or outgoing edges to a single vertex, to all of the vertices. In the second step, which is called apply, we do operations and we do our target computation on that single vertex. And then in the last step, which is called scatter, we just scatter back all those informations or those updates to the neighboring edges. So by leveraging this construction, we defined our own framework, and we call it Oblov graph, which is a secure graph parallel computation framework with differentially private access patterns. So basically in our graph, all of these edges and vertices data, they are encrypted, so nobody can see the content of them. But during this gather and scatter operation, when we are touching these nodes and getting back to the edges, so we are revealing the edge structure, right? So we have to add noise as in the form of dummy edges to this graph, and then we can do our guess operations applied on this graph. So this is the main overview of our framework. So in the first step, we do the dumb-gen, we do it in the garbled circuit or in the secure computation, and we do it only once. So then in the second step, we do the oblivious shuffle. We obliviously shuffle all these elements, the dummy elements, into the real ones. We run the gather and apply operation, and then we have to do another shuffle, then scatter, because between the gather and the scatter, since we are touching both sides of these graphs or both sides of these edges, so we have to hide this access pattern or hide the edge structure in between. So that's why we have two oblivious shuffles. So the practical results that we achieved, we run our framework and we run it for different benchmarks in our paper with the same set of parameters that a graph C targeted. And we had two computation parties. Each of them had 64 processors with the parameters that we had almost 6,000 users, 4,000 movies, and 1 million ratings for movies. So epsilon, which is the differentially private parameters, it is 0.3. And delta, we get it to be negligible function, close to negligible value to the minus 40. So the best result that GraphC achieved, it was 13 hours to do this computation using a real-world dataset, movie lens dataset. And we reduced it down to 2 hours. And with some of the code optimizations, we could bring it also less than 2 hours. So to conclude my talk, so we showed that differentially private leakage is very useful, and it opens up opportunities for more practical and more efficient protocols. And also, we identified a class of computations that could benefit from this relaxation. And we show that differentially oblivious algorithms are very faster and more practical than fully oblivious ones. So by just letting that security notion to be relaxed a little bit and proving that that amount of information that is learned by the attacker is preserving differential privacy, we could achieve more practical and faster algorithms. So thank you very much for listening to my talk.
Hi. At some point, you say you reduce a problem to the histogram by adding fake elements, right? But if you only add like when you actually add Laplace to the histogram in the classical setup, you don't just add elements; you also like remove some randomly, right? So how do you deal with this in your work?
Exactly. So let me actually get to. So that's a very good question. So basically, for generating the noise and our dummy elements, we had the problem of we had to do it in secure computation. So we had to modify that distribution that we wanted to use. We used a two-sided geometric distribution, and we modified it a bit to be able to do it in secure computation. Also, because the access pattern, it is not just the output, similar output that you mentioned in the histogram problem. We could have negative or positive noise. We cannot accommodate negative accesses. We cannot remove from the accesses. So what we did, we shifted that distribution to the right to accommodate to have all of the noises to be positive values. So that's why we have a lot of overhead as compared to, for example, other differentially private histograms, because we had to add, for example, 2 alpha noise at the beginning and then remove from that to compensate those negative and positive values.
So maybe a very quick question. There is, I think, a related work which has come out recently by Ellen Shai, and could you kind of try? It looks very similar, at least from what I read. Could you summarize a bit the relationship or differences between the two approaches, if you're aware of this work?
Yes, actually, I read their paper, and since we were discussing our approach previously with them, and we worked almost, so our paper was almost predating them. So what we did in this work, we focused on this relaxation, and then we identified a class of computations that could benefit from this relaxation. But in their work, they considered some computations or some algorithms that has lower bounds, known lower bounds and upper bounds, and they provide, with their theoretical result, they provide lower bounds and show that, for example, for some of the algorithms that, for example, like non-comparison based sortings, they could achieve better results for specific short key, like in sorting arrays. And so the main difference is that their result is more theoretical results, and also they're submitted to their algorithm conference.
Okay, thanks.
Oh, sorry, one more quick question here. Hi. So for when you're applying the function, you add some dummy padding and you add some noise here to get some noisy histograms, right? Mm-hmm. So my question is, for the accuracy of the final result, how is that? Are you able to get precise results by sort of removing the padded the noise, or is there some sort of accuracy trade-off that you're making here?
So basically, because we don't add the noise to the output, so the output we keep it encrypted or secreture. So the exact we expect the exact values in the output, but if you noticed, those dummy elements that we added, we accompanied it with just one single bit to differentiate between from the real elements. Right. So when we are running this computation in secure computation, we use those bits to add or remove that element from the addition. So for example, when we are adding only the single bit, one bit, right. And we are adding 0, so it doesn't have the effect on the results.
Okay, great, makes sense. Thanks.